Hola, buenas tardes. Bienvenidos a la Ciutat de les Arts y les Ciències. Antes de comenzar, quería indicarles el nuevo sistema de auriculares que tenemos. En las mesas tenéis a la derecha el idioma seleccionar. Bueno, a la derecha del todo hay un botón más grande, que ese será para cuando hagáis alguna pregunta, conectar el micrófono, que ahora todavía no está conectado. Luego, a la derecha tenéis el idioma y a la izquierda el volumen. Conectáis los auriculares en la clavija y, bueno, eso es todo. Bueno, como decía, bienvenidos a la Ciutat de les Arts y les Ciències y bienvenido al British Council, que comenzamos con ellos la primera conferencia de astronomía. Y como sabéis, con el British Council tenemos una estrecha colaboración desde hace muchísimos años y siempre nos traen unos conferenciantes de primer nivel. Hoy tenemos a Belén Fortea, que es la responsable del programa de ciencia del British Council España, y ella va a ser la encargada de hacer una pequeña presentación de nuestra ponente de hoy. Muchas gracias. Cuando quieras, Belén.
Buenas tardes, bienvenidos a todos a esta charla sobre océanos, hielo y fuego, las misteriosas lunas de Júpiter, donde tenemos el placer de contar con la presencia de la profesora Emma Bunce. Emma Bunce es catedrática de Física del Plasma Planetario en la Universidad de Leicester y, entre otros premios, ha sido galardonada en el 2002 con el prestigioso Royal Society Wolfson Research Merit Award, otorgado por la Royal Society a la mejor tesis del año. Hasta la fecha ha publicado alrededor de 95 artículos científicos y su trabajo ha obtenido reconocimiento tanto a nivel nacional como internacional. En la charla de hoy nos va a hablar de las propiedades básicas de las misteriosas lunas de Júpiter y de la futura misión de la Agencia Espacial Europea, el JUpiter ICy Moons Explorer, que recorrerá Júpiter y realizará múltiples visitas a Europa y a Calisto y que será la primera nave espacial en orbitar la luna helada Ganímedes. La misión se lanzará en el 2022 y llegará al sistema Júpiter en el 2030. Muchas gracias a todos por venir, no me extiendo más. Espero que disfrutéis mucho de la conferencia, que creo promete ser apasionante. Gracias.
Thank you very much, and good evening, everyone. It's a real pleasure to be here to speak to you all this evening. As you've just heard, I'm going to be talking about the Galilean satellites tonight, and I'm going to be talking about the Jupiter system a little bit more generally. But my role is, I have two roles at the moment, one at the University of Leicester, where I'm studying solar system bodies in general, working on a few different missions in the solar system, and I'm going to be focusing on a future mission to Jupiter in this talk this evening. And my other role is that I am the incoming president, so I'm the president-elect of the Royal Astronomical Society in London. So I have sort of two hats that I wear at the moment. So starting at the very beginning, as you move outwards from the Sun, Jupiter is the first of 4 gas giants in our solar system. And as I'm sure many of you will know, it's by far the largest planet in the solar system. It's bigger than 10 times the size of the Earth. And amazingly, it contains 2/3 of the mass of all the planets in the solar system put together. So it really is, in many ways, the planet of superlatives. So you're going to notice a theme in my talk tonight. It rotates faster than any other planet. So despite its giant size, it rotates once on its axis in just 10 hours. So it rotates very quickly. It takes 12 years for Jupiter to orbit around the Sun because its orbit lies 5 times further away from the Sun compared to the Earth. You'll probably be familiar with this view that's just unfolded onto the screen. Jupiter's atmosphere is quite famous, and it's one of the most dynamic atmospheres of the solar system. Famous for the bands, the different color bands you can see, the light and the sort of orange bands that you see, and of course, the Great Red Spot being one of the most famous features of Jupiter's atmosphere. And this is a long-lived storm that's been raging in Jupiter's atmosphere for hundreds of years, and as long as really people have been observing the planet. Now, Jupiter itself has about 80 different moons. Some of them are extremely small, very difficult to see from the vantage of the Earth, for example. But 4 of them are incredibly famous, and those are the 4 largest moons of Jupiter, and they're going to be the focus of my talk this evening. And in fact, I think it's fair to say that the more we learn about those moons of Jupiter and the Jupiter system itself, the more we change our view of how our universe works in general. So there's many important processes that are going on in the Jupiter system. So I'm going to introduce you to the most spectacular of Jupiter's moons this evening. So first of all, we have fiery Io in the bottom left. We then have smooth, icy Europa. We have giant Ganymede, planet-sized Ganymede, in fact, and I'll come back to some details later on, and then scar-covered Callisto. And orbiting very close to Jupiter, they're akin to a solar system in miniature with Jupiter at the center. Now, these 4 moons were discovered about 400 years ago, and since that time, they've been studied by telescopes. You can see them with binoculars, but also they've been studied with spacecraft going through the solar system, for example, Voyager, and also by a dedicated mission to the Jupiter system called Galileo. And a lot of what I show you tonight comes from the results of the Galileo mission. So I'm going to introduce you to some of their fascinating properties, and in particular I'm going to focus on properties of the moons that relate to both gravitational effects, the effects of gravity, and the effects of electromagnetic fields, which is my personal sort of background expertise in research. And I'm going to tell you about a new mission which we've come up with called JUICE, the JUpiter ICy Moons Explorer, and what we're going to be doing with that mission, as you've already heard, in 2030. So before I talk about the future, I'd just quite like to go back to the past, because I have some really nice animations that I wanted to show you. So if we go back around 400 years ago, in around 1609, this Italian scientist, Galileo Galilei, was developing a new type of telescope, a new design of telescope which actually allowed a better magnification of the sky than was currently possible to be done anywhere else in Europe. And what he saw with his new design of telescope actually changed the way that we viewed our universe. So at the time, the popular belief was that the Earth was the center of everything. So everything orbited around the Earth. The entire solar system was focused with Earth at the center, and this was known as the geocentric model of the solar system. And that model had been proposed by the ancient Greeks, for example, Aristotle. And any evidence that went against that geocentric model would have been very unpopular at the time. And having designed this powerful telescope capable of magnifying objects in the sky by 20 times, Galileo began a set of observations of Jupiter, which led to an amazing discovery. So what I'm just showing you in this slide is, at the top left, this is an image of Galileo's journal. So these are the diagrams that he was drawing when he was making his observations with his new telescope. And on the right-hand side, this is the publication, Sidereus Nuncius. So this was his write-up of his notes that he made during those observations. And I think this is, for any scientists in the audience, I think this is quite nice to see that my lab book at university was always quite sort of messy and difficult to understand, and then eventually you write it up into something nice and neat that people can understand. So you can see the notes that he made in his journal, and then the publication to tell everybody about what he had found. So let me explain what's underneath. Here we have a reproduction of the sketches that are taken directly from his publication. So these are his drawings, just reproduced. And above, you can see Jupiter and 4 objects. And these are actually the positions of the Galilean moons, which we now understand, and that we understand how they move and their orbits. But it's the positions of these moons at the exact time that he made his observations. So, and this has been done by Ernest Wright from NASA Goddard Space Flight Center. And he went through all of the observations with the dates and the times and made the calculation of where Jupiter was with the 4 Galilean satellites that we now understand how they move. So it's really interesting to compare what Galileo saw with what we now understand to be a picture of where the moons would have been at that time. Okay, so hopefully that's clear as to what those diagrams are showing. So on the first night of his observations, on the 7th of January in 1610, Galileo observes Jupiter here, and he notes in his journal that he sees Jupiter in the middle of a line of stars, which he notes as being, noticeable, unusual. And so he thinks those are 3 fixed stars that are forming this striking pattern. On the second night, Galileo observes Jupiter to the left of these 3 moons. And notice here that he doesn't capture the 4th moon over on the left-hand side there. So at this point, he thinks he's recording the movement of Jupiter relative to the background stars. Okay, so on the next night, after being in the middle of the stars and then to the left of the stars, he now sees Jupiter to the right of the stars and notes that it's a very puzzling situation that Jupiter appears to be moving in the wrong direction compared to the background stars, and he can't understand why this pattern is occurring. Interesting things to note with this picture, here you can see he records 1 star because his telescope can't resolve that there are 2 objects. And here you can see that he's recorded Jupiter and not this object because, again, his telescope is not strong enough to resolve 2 objects. And again, you can see we have the same effect here. We've now got 2 of the moons in eclipse in front of Jupiter, and so again he sees 2 stars. On the 13th of January, you can see here that Galileo actually observes 4 stars for the first time. So he's able to resolve each of the objects, and he notices this pattern for the first time. So he continues his observations over the next 8 weeks, and they're just playing out at the bottom here. And over that time, he manages to work out that these objects are moving with Jupiter. They can't be stars because they're moving with Jupiter in the sky, and therefore he concludes that they're not stars and they must be in orbit around Jupiter. And of course that's a significant result because of the geocentric model, which was how everybody believed the universe worked at the time. This was contrary to that particular belief, and so his results were quite controversial, and as you may well know, actually some of his work here got him into quite a lot of trouble as he tried to defend his observations and his findings to say that this is what he believed. This and other work that he was doing showed that geocentric model was not a true picture of the way the universe worked. So I think it's really fascinating to go back to his observations and his drawings from his telescopic observations in 1610 and use our knowledge of what we now know about the moons and come up with an understanding of what he was seeing in his journal observations. So I don't know if any of you have ever done this, but if you have a very good pair of binoculars or a telescope, then you can also see the Galilean moons, just like Galileo did. And this is a nice sort of amateur or citizen scientist observation of Jupiter, and you can clearly see these 4 moons lining up, just as Galileo would have seen. Now, obviously, the better telescope you have, the more expensive telescope usually that you have, means that you get a better view. But there's only so much you can do with remote sensing. So remote sensing is when we're observing something that's far away, rather than actually traveling to the place to make observations. So there's only so much you can see with remote sensing. And so what we actually need to do is to send robotic spacecraft to Jupiter so that we can get a much closer view of the system. And it's interesting to think about what we can do if we actually go to the destination and make close-up observations. So what we do is we improve the view significantly. Okay, so I've already introduced you to the basic objects. This picture is obviously not to scale in terms of the distance, but the approximate sizes are correct. So most of what I'm going to show you, as I mentioned already, comes from incredible discoveries from the NASA Galileo mission. Okay, so if we just take a look at some of the numbers, what we have is Io, which is the closest moon to Jupiter, and this orbits at around 6 Jupiter radius from the center of Jupiter. Okay, so this is not to scale, but 6 Jupiter radius, what does that mean? A Jupiter radius is about 71,400 kilometers, so about 11 times the size of the Earth. Okay, so Io sits at 6 Jupiter radius and takes a little under 2 days, to Earth days, that is, to orbit around Jupiter. And Europa, which is the smallest of the Galilean moons, sits at 9.5 Jupiter radius, so further away from Io, and orbits in 3.6 days. Ganymede is by far the largest of the Galilean moons at 5,262 kilometers. What does that mean? Well, that's its diameter, so it's about half the size of planet Earth, and it's actually bigger than the planet Mercury. So it truly is a planet-sized moon, and it's by far the biggest moon in the solar system. And then we have Callisto. Sorry, just to finish that. Ganymede orbits at 15 Jupiter radius from the center of Jupiter and orbits with a period of 7.2 days. And then we have Callisto on the outside, which again is very large actually, smaller than Ganymede. It's the third largest moon in the solar system, so with Titan in second place. And its orbital distance is out at 26.5 Jupiter radius and takes 16.7 days to orbit Jupiter. So why am I telling you all these numbers? You know, they're not particularly interesting perhaps, but maybe some of you will have noticed that there is an interesting pattern in the orbit period. So that's the amount of time it takes for the moon to orbit around Jupiter. So what you can see is that Io takes 1.8 days, Europa takes exactly twice that time to go around Jupiter, and Ganymede takes exactly twice the time that Europa takes to go around Jupiter. And Callisto doesn't quite fit the pattern, but it's reasonably close. So you can see that there's a very interesting effect that has evolved in the system. And in fact, it's one of the effects that causes some of the most fascinating phenomena that we see in this system, and that's the effects of gravity. So the effects of the gravitational pull of enormous Jupiter at the center of this miniature solar system, but also the effects of gravity of the moons themselves. As they're moving around Jupiter, they tug on each other. Okay, so what you can see here is an animation of the motion of the three moons that obey the pattern. Okay, so you've got Jupiter at the center, we've got Io going around here, and then Europa, and then Ganymede. And what you can see is that for every 4 orbits that Io makes, Europa makes exactly 2, and Ganymede makes exactly 1 orbit. And so this is called a Laplace resonance pattern. And it has some interesting effects, very interesting effects on the moon. So if you watch the animation, every now and again what you'll see is that they all line up. And when they all line up, they have a significant effect on each other. So you can imagine that out in the outer part of the orbit here, that's where we have planet-sized Ganymede with a significant gravitational field, and that has a significant effect on the moons inside Ganymede's orbit, particularly Io and Europa. Okay, so we have Jupiter's gravity having a very strong effect on the moons, but also the moons affecting each other. And actually what that does is to flex the surfaces of the moon. So it actually changes their shape from spherical shapes. And when they all line up, the gravitational field pulls and pushes on the moons and produces something called solid tides. Well, that's what we call it, not knowing what else to call it, really. So it's the same effect as we have on the Earth, the moon has on the Earth, that creates the tides in the oceans. But here we have solid tides, so the surface is moving. This is kind of hard to believe that this really happens, but the effect is significant, and Io's surface moves by about 100 meters, and at Europa, the surface moves by about 30 meters. And that produces heating to the interiors, which then has some very interesting effects. Now, the second thing which is of great interest in terms of understanding the phenomena that we see relating to the Galilean moons is all to do with electromagnetism. Okay, so let me try and explain how this works. As I said, Jupiter is the planet of superlatives, so you won't be surprised to hear that it has by far the strongest magnetic field of any planet in the solar system. the strength of Jupiter's magnetic field at the surface, in quotes, of the gas giant is 20 times stronger than the Earth's magnetic field at the surface of the Earth. Its magnetic moment is about 20,000 times stronger than the Earth's. So Jupiter's magnetic field is generated deep inside the planet, and the planet is rotating once every 10 hours. And so the magnetic field is rotating with the planet. So this very strong magnetic field is spinning around once every 10 hours. Now, the moons themselves are moving, as we saw in those numbers, at a much slower rate than that. So they take 1.8 days or 3.6 days to orbit around Jupiter. And so what we have then is the magnetic field sweeping past these Galilean moons and interacting with them as it does so. So the rotating magnetosphere, or the rotating magnetic field, and magnetosphere, which is the larger magnetic environment of Jupiter. I'll come back to describe what the magnetosphere is a little bit later on. Rotates past each of these moons in the magnetosphere, in the environment of Jupiter, and each one has its own special interaction, which we have observed. Okay, so what I'm going to do now is to go through each of the moons in turn and tell you a little bit about the effects of gravity and electromagnetism in each case and what we've observed and why we are so desperate to go back to the system to learn more about how it works. So, because of this pushing and pulling of the surface of Io, it generates a huge amount of heat in the interior and actually creates a magma ocean underneath the surface of Io. And this flexing of the surface has actually led to the situation that we find that Io is the most volcanically active body in the solar system. Somewhere up to around 400 volcanoes have been observed on Io's surface, and at any given time, up to 100 of them can be active. So you can imagine what the environment is like on Io. So you can see that Io looks a little bit like a sort of pizza, I always think. It sort of looks a bit like it has little olives on it. The olives are the volcanoes, and the cheese is the effect of these volcanic eruptions continuously resurfacing Io with sulfur and other unpleasant materials. Now, these volcanoes were discovered by the Voyager mission in 1979. So they were viewed, this is an image taken by Voyager, and you can see here, this is the discovery image. So when people first looked at the Voyager data, the images from Voyager, they weren't expecting to see active volcanoes. And the person who first looked at these images thought there must be something wrong with the image, but then eventually realized what they were looking at, and they were looking at a volcano erupting. So I've already mentioned that Io is thought to have some iron core surrounded by a magma ocean and this crust around it with hundreds of active volcanoes. And most of the observations that we have came from flybys that were done by the Galileo mission between 1995 and 2003. So here's a little movie on the left-hand side. I hope you can see that on the screen. This is actually a sort of animation of images that were taken by the New Horizons spacecraft on its way to Pluto. And amazingly, at that point that New Horizons flew past in 2007, Tvashtar volcano in the northern hemisphere very nicely decided to erupt in a spectacular fashion for New Horizons to image. And so what you can see, and is published in an interesting paper by Spencer et al. In Science, you can see that these plumes actually reach up to around 300 kilometers from the surface of Io. So actually what happens with these continuously erupting volcanoes, it creates an atmosphere of neutral material that's come from the volcanoes that is around Io itself. And what you can see through telescopic observations made by Schneider and Trauger, for example, you can see, if this is Jupiter in the center, you can see that the material that's coming out from Io is in an environment around Io itself, but then actually spreads out all the way along its orbit and all the way around Jupiter. Initially, that material is neutral, so it's atoms that have come, or particles that have come out from the volcanoes themselves. But over time, those particles become ionized, so they become charged material. And this creates something known as the Io plasma torus, which you can see here. These are sulfur ions measured remotely from the Earth. Now, interestingly, the plasma torus, once the material is charged or ionized, it senses the magnetic field of Jupiter, and so it gets swept up with Jupiter's magnetic field. And so the magnetic field of Jupiter rotating around actually drags the ions with the magnetic field and spreads it into a plasma torus which exists all the way around the orbit of Io. One interesting fact about Jupiter's magnetic field is that it's tilted with respect to its rotation axis. So there's a 10-degree tilt in the field. And so as the field rotates around, the plasma torus actually wobbles around, and you can see that effect in these observations of the plasma torus. So that environment around Io actually creates a really interesting effect. So there's a plasma torus containing charged particles, sulfur ions and electrons that have been separated. And those are guided by the magnetic field and swept around, rotating around with this 10-hour rotation of the magnetic field. But what happens is that locally to Io, that material, that magnetic field, actually interacts with the local plasma production at Io and creates a very interesting effect. So what we actually see, this is Io here. If we were to follow the magnetic field line that connects through Io, so the field line that comes out from Jupiter's northern hemisphere, connects through Io, and then goes into Jupiter's southern hemisphere. If we were to follow this magnetic field line, we actually find, amazingly, that we reach the point in the atmosphere and there is a footprint of Io's interaction with the magnetic field, so with the electromagnetic environment. And this is known as the Io footprint aurora, and I'll just show you in a little bit more detail. This is an image taken with a slightly more powerful telescope than Galileo's telescope. This is the Hubble Space Telescope, and we often use the Hubble Space Telescope to point at Jupiter and Saturn, specifically to look at their aurora. So obviously we have aurora here on the Earth, and it works in a particular way that is driven by the sun's interaction with our planet and its magnetic field. But one of the features of Jupiter's aurora here is related to Io. So what you see is you see a spot at the foot point of Io, and you see a tail that comes around. And in fact, some images from Juno, which is another mission to Jupiter, which is currently orbiting the planet, shows that this tail can go all the way around, almost all the way around the polar cap. And in fact, I just want to very quickly show you some of the Juno observations. It's a little harder to see the context compared to that Hubble image where you could see the whole polar region. Here you've got a zoomed-in image on Io's tail. But Juno's cameras have revealed that there is enormous amounts of structure in the Io footprint and in the tail. And you can see here there's a sort of vortex pattern in the tail, and even a splitting of Io's tail. And people are still working on their theories as to how that observation can be explained. So to go back to Jupiter's aurora, we haven't finished with Io's effect on the system, because Io also affects the main aurora that we see. Okay, so if you just look at the auroral emissions of Jupiter and compare them to the Earth's aurora, which is shown on the right-hand side, you would think that they look quite similar, and maybe they are created in the same way. The physical processes are the same, to do with electrons impacting into the atmosphere and causing it to glow at different wavelengths. But the way in which the aurora is driven is very different at Jupiter compared to the Earth. I should just say that, of course, Jupiter's aurora is the brightest aurora in the solar system. It's 1,000 times brighter than the Earth's aurora. And this picture of the Earth here is approximately to scale. So you can see that the entire planet Earth would fit about 3 times across Jupiter's auroral region. So it gives you a sense of the scale of these powerful phenomena. Okay, so just a little bit more about the magnetosphere of Jupiter. So the magnetosphere of Jupiter itself is the extended region of Jupiter's magnetic field, so extending far beyond the Galilean moons. And it's formed when the Sun and its magnetic field, moving out through interplanetary space, interacts with Jupiter's magnetic field. So this causes a cavity to be formed that contains and is controlled by Jupiter's magnetic field. So when the Sun's magnetic field and plasma, the solar wind, reaches the day side of the magnetosphere, it squashes the front of Jupiter's magnetic field, and on the night side, it stretches it out into a long tail. And in fact, Jupiter's magnetosphere is so big, if we could actually illuminate it and see it in the sky, it would be 5 times the size of the Sun. And Jupiter's magnetic field, this is Jupiter's orbit. Jupiter's magnetosphere and its tail is thought to actually extend all the way to the orbit of Saturn. So it's an enormous object, it's an enormous region of space, and hence it's sort of, you can understand that it's powering this very bright and dynamic aurora. So just a quick explanation of the auroral oval, which is also linked then to Io. So Io produces around a ton per second, 1,000 kilograms per second of plasma into Jupiter's magnetic field. And that plasma is swept up in the rotating magnetic field of Jupiter. So these white lines represent Jupiter's magnetic field, and this region represents the region of plasma. So as the plasma is moving around quickly, it wants to move outwards, so it spreads out through the equator and creates what's known as a magnetodisk. So it's a thin disk of plasma that sits at the equator. Now, as that material is spinning around with the magnetic field, it's trying to keep up with Jupiter's rapid rotation of 10 hours. But as it moves outwards, it finds it harder and harder to keep spinning with the planet, and the material starts to slow down. And as it slows down, it bends the magnetic field. So it actually curves the magnetic field of Jupiter, and that generates an electric current system that connects the whole of this region of space in Jupiter's magnetic field to the auroral regions through an electric current system which goes up the field lines here, through the equator, down the field lines at the top, and closes in the upper atmosphere of Jupiter. And it's this current here, where the current is going up and electrons are going down, that is thought to produce this very bright main auroral oval that you see at Jupiter. So it's all down to Io. It's all because Io is producing this ton per second of material, and that's because of the gravitational effects of the moons and of Jupiter. So all of these phenomena are working together to create this spectacular system. Okay, so Europa has a very different surface, a very smooth surface and icy, but also rather unusual looking compared to a lot of other bodies in the solar system, a distinct lack of impact craters. You can also see that there are many cracks and ridges across the surface, and we see regions of this very pale, icy surface, some of it quite blue looking, and then this sort of orangey brown material that we see that looks to form in these regions, these linear cracks and ridges that are crisscrossing the surface. So even from images, there's always been an indication that Europa may have geologic activity. So it may have processes which are cracking the surface and then refreezing, and possibly subsurface water. So these images were taken across the Galileo mission, and you can see that there's a whole range of different types of geology which you see on the surface, depending on which regions you look at. But you can see this evidence for cracking of the surface, and some of the regions look like they've been pulled apart and then frozen, and if you move the images around, you can almost put the pieces back together like a jigsaw puzzle. Interestingly, though, the evidence, the strongest evidence that we have for an ocean underneath the icy surface of Europa actually comes from magnetic field measurements at Europa. So when Galileo, the mission, was flying past Europa, if there was nothing interesting going on, you would expect to see the magnetic field of Jupiter in the background. So as you fly past Europa, you wouldn't necessarily expect to see a strong effect if there was no interaction between Jupiter's magnetic field and Europa. But what happened when Galileo flew past multiple times is that a systematic pattern of observations emerged that indicated that there was a magnetic field that had been driven by Jupiter's magnetic field interacting with Europa. And the way to explain this is that if there is an ocean underneath the icy crust, and if that ocean is salty, then it's a conducting ocean, it's a conducting body moving in Jupiter's magnetic field, and that motion of a conductor within a magnetic field generates another magnetic field. And so that's what we're seeing, and that's how these observations have been interpreted. One indication that we have, because the question is, maybe Europa has its own magnetic field. But if you remember, I said that Jupiter's field is tilted and so it wobbles up and down as it rotates around. That means that within a 10-hour rotation of Jupiter, Europa senses a different direction of Jupiter's field as it wobbles back and forth. And the induced magnetic field seen at Europa switches direction as that field wobbles back and forth across it. And that's strong evidence for that being an induced signature likely to be associated with a global ocean. And I just want to mention this lady. This is Professor Margaret Kibbleson from UCLA, and she discovered the subsurface ocean at Europa, and she was awarded the gold medal of the Royal Astronomical Society in 2019. And she was 90 last year, and she's still traveling all over the world and still involved in future missions to the Jupiter system. So she's a really inspirational character. So the evidence from those observations suggests that Europa's oceans could be 10 times deeper than any ocean that we have here on the Earth. And if you do the calculation, given the size of Europa, that could indicate that there could be 2 to 4 times the volume of water underneath Europa's icy crust compared to all of the water on Earth, which is quite a mind-blowing fact. Well, to be confirmed. So, of course, the fact that there's water, oceans of water in the outer solar system opens up a whole new conversation about habitability. We've often been thinking about habitability, we tend to think of Mars, but this discovery that there's a body of water in the outer solar system that's heated by tidal effects and flexing of the moons, keeping the subsurface liquid, opens up a question about habitability and whether or not these environments could be the best chance of finding life beyond Earth. Okay, swiftly moving on to Ganymede, we then have planet-sized Ganymede, as I've already mentioned. It has an extremely interesting surface, actually, from a geological point of view. For example, it has a unique feature called grooved terrain, and this is unique to Ganymede. And this is thought to be associated with vertical shifting of the icy crust, so this is an icy moon as well. It also has interesting features like these crater chains that you see here, and this was thought to be produced by a comet that was broken up by Jupiter's gravity as it was coming in from the outer solar system and then happened to land on Ganymede's surface. And Ganymede is also thought to have a subsurface ocean and may have an interesting structure in its subsurface ocean where it has what has been referred to as an ocean sandwich, so where you may have layers of ice and water as you go deeper into the surface of Ganymede, but again, to be confirmed. So the Galileo mission, again, with its magnetic field observations, discovered that Ganymede, again, like Europa, has a magnetic field which is generated through the interaction between Jupiter's magnetic field and a subsurface ocean, a conductor. But, interestingly, what makes Ganymede slightly different is that the Galileo observations also demonstrated that Ganymede has its own magnetic field. So a magnetic field that's generated in the core of the moon itself. And as far as we know, that's the only moon in the solar system to have its own magnetic field. If you put a magnetic field of a moon into the magnetic field of Jupiter, and Jupiter's magnetic field is sweeping past every 10 hours, you generate a miniature magnetosphere within a magnetosphere. Okay, I'm going to skip this slide, but if anybody wants to hear the audio file at the end of Ganymede singing magnetosphere, then we can come back to it. But let me just continue. Planet-sized Ganymede also has its own very weak atmosphere, but is thought to have, or it does have, an auroral emission which has been observed by the Hubble Space Telescope. So this is much weaker than Jupiter's aurora, but is an oxygen-based auroral emission, as it has oxygen predominantly in its atmosphere. And then Callisto, again, an entirely different body, so 4 very diverse bodies, all within the same system. Callisto has a very heavily cratered surface, a very old surface, so no indication that it's been resurfaced by any processes like volcanoes or water coming out through cracks and refreezing onto the surface. It has this huge impact crater called Valhalla, which is one of the biggest impact craters in the solar system. And it's thought that Callisto's interior is undifferentiated, so there's no separation of the heavy elements towards the center and a lighter mantle, but that the body may well be undifferentiated. And it's also thought that Callisto may have a subsurface ocean, so there are hints from the data so far that that may be the case. So all of this leads us, as I mentioned, to think about habitable worlds. So if we're interested in understanding whether or not there's a possibility of some form of life beyond the Earth, it's interesting to think about these bodies that may have significant volumes of water and potential, so that's one of the main ingredients that we know you need in order to have life. So not Io, but potentially Europa, Ganymede, or Callisto. And of course, Europa is one of the favorites for that. So all of this leads us to require that we have a future mission to go back to the Jupiter system. So we currently have the Juno mission there, but that's in an orbit which is designed to study Jupiter itself very closely and is not focused on the Galilean moons. So we came up with, I was very fortunate to be involved in the team of scientists who came up with the mission proposal for the European Space Agency. And this mission was accepted, which is fantastic. And so we will have JUICE, which is a very bad acronym, but it stands for Jupiter ICy Moons Explorer. And the idea is that it will be launched in 2022, will arrive at the end of 2029, and is going to study the system, but importantly is going to be the first European mission to Jupiter and the first spacecraft to go into orbit around an icy moon. And so we're going to be looking at these Galilean satellites and also Jupiter itself. So the mission is going to launch in 2022, and it takes the usual circuitous route to get to Jupiter. So it's going to take a few flybys of different planets in the solar system and 7.3 years of journey to get to Jupiter. So we have to be patient. But once it's launched and arrives in the Jupiter system and goes into orbit around Jupiter, it will then spend the first year focused on looking at Jupiter itself. So we have an opportunity again to study Jupiter and its atmosphere. And then the fun begins as the orbit starts to change to get closer to Ganymede. So as the orbit starts to reduce down, we will have 2 Europa flybys. And Europa is a very difficult body to study because of its location in the magnetic field. It has a very harsh radiation environment. So for the spacecraft and for the instruments on board, it's a very challenging environment. So it's in red, and there's only 2 flybys. So we protect our instruments, but we hope that 2 flybys will give us significant scientific information. And then as the orbit reduces closer to the inner part of the system, we're going to have an inclined phase. So the orbit will lift up and incline to the equator so that we can look down onto the equatorial plane that contains the moons, and we can also look at the upper atmosphere, the polar regions of Jupiter. And then as we reduce down, we will have 10 Callisto flybys, close flybys of Callisto, and then we move to the last part of the mission, which is focused on Ganymede itself. And so all of those tentative results and our understanding of how Ganymede works really needs to be confirmed. And the only way that we can do that is to actually go into orbit around Ganymede. So we want to understand how its magnetic field works, how we can model its magnetic field that's generated within the body itself, its gravitational field, and also the field that is driven by the rotation of Jupiter's magnetic field past the body itself. So the field, the magnetic field that's due to the subsurface ocean. If we go into orbit around Ganymede and study that signature over a long period, we can actually work out things like the depth of the ocean, potentially the conductivity of the ocean, and possibly the thickness of the icy crust. So all of those things are possible from a scenario where we're in orbit around Ganymede. So the total mission at Jupiter will be approximately 3 years and will end with the spacecraft impacting on Ganymede itself. So previously it was thought that life could only exist in the region of space that we call the Goldilocks zone, where the temperature is just right to have water on the surface of the planet. So exactly where we are, sitting on planet Earth in the Goldilocks zone. But the source of the energy, or the source of the heat that allows life to survive on Earth, of course, comes from the sun. And so the Goldilocks zone is driven by the proximity of our planet to the sun. It's in just the right place, not too close and not too far away. However, these deep ocean habitats that we have discovered through missions like Galileo open up an entirely new possibility for thinking about the habitability of these bodies. And in fact, I've mentioned the Jupiter system, but there are also moons in the Saturn system, Enceladus and Titan, that also have subsurface oceans. And this is a picture of water spewing out of Enceladus into the Saturn system. So we've seen the evidence that this occurs and exists. So it's changed our view of possible habitats in the solar system. We also know that there are likely to be billions of planets elsewhere beyond our solar system, and just over 4,000 extrasolar planets have now been confirmed, with new missions to study them, expecting to reveal more and more information about them. And of course, one thing we want to know is whether there are planets like our own where life could develop. So with this new knowledge of water worlds within our own solar system, and of course Jupiter itself, we can use these as analogues for the extrasolar planets that are being discovered. We now know there are all sorts of different types of extrasolar planets, and this has probably even changed since I made this slide. Jupiter itself is a type of extrasolar planet, hot Jupiters, and it's thought that water worlds have been discovered. So it's a tantalizing area of study. But of course, we can't easily go to extrasolar planets. So what we can do is go to these water worlds within our own solar system and gain insight into how these bodies beyond our own solar system might work. So that's just a summary of all the spectacular science that we're going to do with the JUICE mission, looking at Jupiter, looking at the magnetic environment, how the processes couple together through the gravitational fields and through the electromagnetic fields, and of course, studying the satellites in particular and how they operate in the system. And of course, this is the next logical step in our exploration. We've gone from the discovery of these bodies 400 years ago through to the first insights from missions like Voyager, where we first saw the volcanoes on Io. We now also understand, since many years ago, that there are deep habitats that exist in our own oceans that are able to thrive in the absence of any sunlight. And so we know that it's possible to have life existing and thriving in regions that don't agree with our simple ideas about the ingredients that are required. We then have the Galileo missions to Jupiter, the Cassini mission to Saturn, the discovery of extrasolar planets, and indeed the discovery of the first extrasolar water worlds. And so we think, and luckily ESA agreed, that this is the next logical step in terms of our exploration, to send a spacecraft to go to the Jupiter system and study one of these bodies very closely will significantly increase our understanding. And then looking to the future, if we can first of all get very close to Ganymede in our 500-kilometer orbit, eventually we'll be able to understand the surface much better and potentially send landers to go down onto the surface of Ganymede or Europa. So I'll leave it there. And I always show this picture of Galileo at the end of my talks about Jupiter, because I always think that I can't help but wonder what he would think of all of these things that we now understand about these bodies that he discovered some 400 years ago with his telescope. So thank you very much for listening. Thanks. I think there will be a chance for questions. Is that right? See how this works.
Vamos a dar paso a un pequeño turno de preguntas. Tienen a la derecha el botón para activar el micrófono. Levanten la mano y activen el micrófono cuando quieran realizar una pregunta.
Aparte de la teoría de la existencia de océanos salados bajo capas de hielo, apoyada por su teoría del electromagnetismo, que es la única que ha mencionado, si hay otros indicios, aparte de ese, de que pueda haber agua líquida. Yo, por ejemplo, he leído que con el Hubble creo que se detectaron unos penachos que podrían ser proyecciones de vapor de agua al estilo de geysers, por ejemplo, o que otras pruebas hay que apoyen, aparte del electromagnetismo, la existencia de agua líquida.
Okay, I should do my best to answer that question. I think I got the gist of the question. So, other evidence for oceans comes from imaging, for example. So some of the features that you see on the surface give an indication that for example, Europa, where you can see that the surface has maybe cracked and refrozen, so I mentioned that one. Another obvious signature of a global body of fluid underneath the icy crust is actually from the gravitational field. So for the Cassini mission, the spacecraft was able to get very good measurements of the gravitational field of Enceladus, so that we now understand from those measurements that in order to explain the gravitational field complexity, you have to have a global body of water which decouples the interior from the icy, so you get a sort of wobble from the icy crust compared to the interior. And also with Enceladus, you have evidence of the plumes of material that are coming out from the cracks on the surface.
Y esas plumas o esos penachos que dicen contendrían a lo mejor iones de hidrógeno y oxígeno, puede ser, y por eso se deduce que puede haber agua, ¿es así?
The Cassini instrumentation was designed to measure neutral particles and charged particles. So there were different mass spectrometers and different types of spectrometer that could measure those particles. So we have a really good understanding of the material that has been thrown out in those plumes at Enceladus. And it consists of dust and ice and water. And so we know that those sorts of materials are coming out from underneath the surface, but also there are other organic compounds as well, which are obviously very interesting in terms of the chemistry of that, geologic activity.
Well, I want to speak in English, okay? So the thing is that what she has asked, okay, she was referring probably to Enceladus and to Saturn, because Enceladus is a Saturn moon, okay? But now we are talking about Europa in Jupiter. And my question is JUICE, the mission of European agency, having this kind of instrumental to detect maybe some plumes in Europe, not in Enceladus, but in Europe?
Yes.
Okay, so please
So,
explain.
Yeah, so there are two things to say. You may be aware that there were some Hubble Space Telescope observations of Europa, which give fairly good evidence that there may be a plume at Europa that could be similar to the plume that we see at Enceladus, although I think it's not always present. So people have made observations on a number of occasions, and the plume has not always been present. So the instrumentation that will be on board JUICE will be capable of looking specifically for those plumes on Europa. In particular, the ultraviolet spectrometer will be able to make observations, and we may find things that we're not expecting, which is exactly what happened with Cassini. So.
And around what time? Because you have said that the flybys are only around 36 days. So what time is the frame that they can make these measurements? They can look at Europa?
I don't know the exact plan, but it doesn't have to be at the time that we're doing the flyby of Europa. And of course, if we're really lucky, there'll be a plume and we'll fly through it. It could happen. So there are possibilities that during the actual flyby of Europa, we could see evidence to support the existence of a plume. But it might be that you can make observations of Europa remotely from other parts of the orbit during the wider 3-year tour. So the team are looking exactly for those opportunities where there'll be the best viewing opportunities and with the conditions such that you can get the best chance of observing a potentially quite weak and sporadic in terms of time plume existence.
In regards with the previous question, what will be the main instruments aboard the spacecraft?
For the JUPiter spacecraft?
Yeah.
So there are instruments to study the surfaces of the moon, so imaging instruments. There are infrared, there's an infrared spectrometer, there's an ultraviolet spectrometer, so you can do a variety of different observations with those sorts of instruments. And the capability to make very accurate gravitational field measurements. And then there is also a magnetometer. And the magnetometer is on a very long 10-meter boom. So that's one of the instruments that I work on, so I'm quite familiar with the magnetic field. But the challenge of the observations for Ganymede and Europa are, well, Ganymede in particular, is that the magnetic field is very complex and it's changing with time. And we want to study that, but you have to be able to measure changes in the field that are very, very small, maybe a few nanotesla, which is a very small amount of magnetic field. So the instrument being on a very long boom is extremely important for the magnetic field instrument because the main spacecraft instrumentation can generate magnetic fields, and so the further away the magnetic field instrument is from everything else is really, really important. So that's a significant aspect of how accurate and how good the resolution of the magnetometer will be. And then as well as the instruments that will be studying the bodies themselves, there are also instruments to study the charged particles in the magnetic environment of the planet as well. And I'm sure I've forgotten some others, but I think there's 10 or 11 instruments on board. So it should be fantastic, you know, it should be state-of-the-art measurements that have been specifically designed for being in orbit around Ganymede. So that's the real challenge of this mission, is designing an instrument that is capable of making some observations of Jupiter, but focusing on Ganymede as the object that we really want to get the best information from.
Bueno, pues si no hay más preguntas, vamos a dejarlo aquí. Les rogamos que a la salida dejen los auriculares en la base, donde la han cogido al principio, y vamos a darle muchísimas gracias a Emma Bunce por su fantástica charla y sus fantásticos comentarios. Muchas gracias a todos.